Yeah, hey everyone. I'm Daniel, and I'm very, very pleased to be here, actually. It's not the first time I'm in Prague, but yeah, I've never been to this university, actually, I think. And yeah, it's really, really cool to see so much going on here. And today I'm bringing you a talk about something I'm doing a lot in my free time. And it has to do with Linux, but not only Linux, actually. So yeah, I hope you can see the slides good enough from there with a dark background. Anyway, so I'm going to talk about what comes before Linux, or in fact any operating system. And I would like to see some hands now. Do you know any of the other operating systems I'm listing here? Like, who knows the BSD systems? I'm seeing hands. That is good. Who knows Windows? Oh, OK, everybody sort of knows it. Nobody likes it, I heard. Mac OS? Guess also everybody knows it. Who knows Haiku? Nice. Who knows Oberon? Not many people. We can do this again later with a longer list. Who has heard of Plan 9? That was, yeah, 1, 2, or 2.5, 3 hands. Nice. Thank you. So yeah, if you want to run an operating system, you unfortunately need to do a lot of things, which you usually don't see when you just turn on your computer. You know, at some point, you just see your operating system come up, and that's mostly within a few seconds. So yeah, that's what we're going to talk about today. A bit on me. So I'm Daniel, and I work in my free time a bit on a different set of, like, a bit of operating systems, a bit of firmware. I do some, well, reverse engineering in a way, sometimes just because I have to. Yeah, otherwise, in my normal day job, I'm a web developer, and I work on things that run in your web browser in a slightly higher level. And at some point, I created a few projects, like the Fietka firmware editor. If you want to know about it, go check out the website later. The slides will be uploaded, so you can follow all the links I'm presenting here. And I created a larger project, which I call the Platform System Interface Project, which is essentially everything about hardware platforms and operating systems and all the details in between. And that brings us to the topic for today. So I will first talk a bit about bootloaders and firmware. I will try to, give some descriptions of what things are precisely. It's not too easy because, everyone has a bit of their own idea of what that should be, or, what the scope should be. So we're also going to classify things a bit and see, how we can look at it from a sort of mostly neutral angle. I will give you some lists of projects to look into if you're interested in more. And then I will talk a bit about a very important aspect I find for today, which is ownership. And we will talk a bit about sustainability in the same manner. So what are bootloaders and firmware anyway? I guess everybody here knows some part of a bootloader or some aspect of firmware anyway, because usually, when you turn on your computer, you're presented with some sort of selection in most scenarios. And a bootloader is really just a very simple application, and that is an application that is just loading another application. So you just jump from one thing to another. That is the most neutral definition I could find that sort of fits everything. And well, this here is one that is very, very famous. I guess most people here who are running Linux have seen it before. It's the very, very well-known GRUB, so the Grand Unified Bootloader. It's been in use for many, many years now. On more modern systems, you might already be using something else, like SDboot from the systemd project, or systemdboot that was derived from a predecessor at some point. Or you might have been in the embedded space, or on ARM-based systems, you might have heard of something called U-boot, which actually goes way, way back to the late 90s even. Well, so yeah, what I'm showing here is really just a screenshot, from an emulator called QEMU. So this is how you can try out different things. Now let's see if we can sort of fit this bootloader thing somewhere. And I'm saying the bootloader is essentially what is between your firmware and your operating system. When I say firmware here, in this context, I mean firmware for the large compute systems that we have. Firmware can have very, very, very many meanings. It can also be the tiny few lines of code that you might put on a microcontroller. But here in this case, we're interested in compute platforms that are more universal. So here is what I'm suggesting. We put the bootloader in the middle. On the very left-hand side, we have the so-called platform initialization. That is a term used in many places, and that is the really firm part of the actual firmware. So firm, what does it mean, right? It's like the opposite of soft. It's the thing that you cannot really change in this scenario here. So what we're doing there is we initialize something called an SoC, a system on a chip. We fill up some registers as the operating system should expect them. We set up clocks and GPIOs, so that is also what you do on microcontrollers. We also need to do that on SoC platforms today. And well, the most important part, so that we can actually use the many gigabytes of memory that you have, we set up the DRAM controller. When we're done with that, we're ready to use the DRAM, and we can put a bootloader into that DRAM, and the bootloader can itself already be a bit more capable and rich, like the grub that you saw, which has very, very fancy graphics now, you know, not the clunky text, but actual very, very nice appeal. Well, and that then would load your operating system's kernel. It might check for integrity. I'm arguing it should nowadays because, you know, we want to make sure that our kernels are not compromised. And maybe there might be an interactive menu. So like many distributions give you the option to switch back to a previous version when you upgrade to something in case something goes wrong. Well, then comes any of the operating system, like what we just talked about. Linux can be FreeBSD or any other BSD, Plan 9, Oberon, Haiku, you name it. Now, what do we need to have in one of the bootloaders? There are three main components that we need, and those are drivers, parsers, and loaders. So drivers, I think when you first had computer science here, you might be familiar with the concept. It's very, very simple. It just means something that knows how your hardware actually works, right? So it's a component. You talk to the hardware, like that could be, I don't know, let's say a USB port, for example. You need to know how a USB port works. You need to know how the specific USB controller on your platform works. For example, when you want to read from a USB drive, right, that could be where your operating system is. So now you need to understand the bus, you need to understand file systems, and all of that stuff is in there. There are many environments that can provide these capabilities. So for example, in something called UEFI, which is what is implemented in most laptops nowadays, there is something that is called DXE, or also called Dixie. That is the driver execution environment. Already has driver in its name. So that is where, you know, you have like hundreds and sometimes even 1,000 drivers for essentially everything, so that you are very flexible in booting up a system. We can do the same thing with the Linux kernel. So the Linux kernel also has like tons of drivers for virtually anything you can think of nowadays, right? So you can also use that as a boot environment, and we will look at an example in a bit. Then you need parsers. And parsers, you might also know that from other computer science lectures, like, you know, compilers and so on teach you parsers. A parser is actually, in a very, very simple sense, it's just something that reads data and interprets that data in a way, right? It tries to make sense of the data. So it needs to understand data formats. And that is also what we need when we want to load an operating system. So operating systems can be in various different formats. Like in UEFI, for example, there is a format used that is called PE32. In many Unix systems, we use something called ELF. Or it could be just a very simple binary. We can load configuration files that we need to interpret and all of that stuff. Well, that means we also need to be very, very careful with these. And we will also talk about that in a bit. The final thing we need is the loader. So what does a loader do? It's essentially very simple. It needs to understand the protocol of an operating system. In the Linux documentation, for example, you would figure out, like, if you want to load a Linux kernel, what do you actually need to do? That is usually a bit specific per platform, but it's mostly very simple. You put it somewhere in memory, and then you execute it. And, you know, then it depends a bit on the platform, but yeah, let's not go too much into details here. So, yeah, what do you do eventually? When you have something in memory, you just do a jump instruction on most systems, or, you know, it can also be a bit of a different instruction, but yeah, the simple part is you're leaving your bootloader now, you're handing over to the operating system, and it can then take the whole platform for itself. I've talked about this also in a few other places. We had a very interesting project that is called WebBoot. If you want to look at that, that is for booting systems from somewhere on the internet maybe, or a local network or something. There are many implementations of that idea. This was one of them. Yeah, be welcome to have a look at that. Now, I already told you that you need to be careful with a bunch of things here, so let's talk a bit about security, because I saw that during the last years, people started looking a bit more into platform security, and that is especially affecting essentially all the laptops that we have here. Even the computer I see in front of me, I don't really know what's behind it, I just see the screen here, but I'm very sure it's an x86 platform. Might be a tower PC down there or something. Oh, actually, I'm seeing something there. Yep, that looks like Intel. Okay, so that already gives me a bit of a clue of what's in there. Well, firmware, as I said, you need to be very careful with what you do there. It's a huge attack surface, essentially. And I will now narrow this down a bit, because there are some things which you might not be aware of that are actually lingering somewhere in the background when your operating system is running. Here is a very small list of a few incidents from the last few years. Has anybody of you heard of this thing called logo fail? I'm seeing hands being raised. Okay, that is very good. Who has heard of pixie fail? I'm seeing hands again. Okay, not too many, but okay, let me briefly explain this. So that was end of last year when logo fail was published, and beginning of this year when pixie fail came out. So these are two very, very severe vulnerabilities in firmware. And when we say firmware, currently we're talking about the UEFI ecosystem. UEFI is like a large specification that vendors like Lenovo or MSI and so on, they use that and implement their firmware with it. And what they put in there is all the fancy features that you may need. Like Lenovo thought it would be cool if you could have a custom splash screen image when you boot up your PC. That is very nice. Now you need a parser for that image. And guess what? The parser that Lenovo was using was actually quite broken. And it doesn't really end with Lenovo. That was actually a bunch of companies who had similar features, which had very, very severe flaws. So that would mean if you prepare an image and you know how to trigger the vulnerability, you could actually execute arbitrary code. And you could even set that splash screen image just from your operating system environment in some cases, which essentially means with two vulnerabilities in your system, you could have persistent malware on the motherboard, in your laptop. So even if you install a fresh operating system, you throw away your SSD, you take a new one, you would still have that malware. That is not very good. So essentially, you only need an exploit in your web browser. Well, we're browsing lots of websites today, so you can never be really sure. And once you get out of there, you need another exploit in your operating system's kernel. That is 2 steps. I'm not saying that it's too easy, but it's also not impossible, as you might have heard from, other incidents. The pixie fail thing, sort of similar. That was related to everything happening in networks. So pixie is also a boot mechanism, PXE, that's how they usually spell it. And this here is not even related to pixie only. So that is a boot method for networks. But there are also other things going on in the network. And your firmware is actually also having lots of network capabilities like, DNS, DHCP, IPv4, and v6, maybe multiple stacks even. That always depends a bit on the vendor. Very, very dangerous stuff. So, yeah, but it's always, a bit seemingly artificial when people talk about that stuff. So I had a look at that end of last year, and I saw, well, it really works, actually. So I bought a used Lenovo ThinkPad X270. We did some live streams from our hackerspace, and at some point, well, I could see very, very fancy garbage pixels on the screen. And what you're seeing here is actually some leftover parts from somewhere in the memory. That isn't an image I provided myself. I just, put an image in there and then gave it like, I don't know, weird large dimensions. So what the image parser was doing, it was reading past the actual image data, and now you're seeing a visualization of anything I have in memory. If you have some ideas of what, tables and so on in memory look like, you can actually make sense of this. Black means this is all 0 bytes, for example. White means it's all, all the bits are being set. So yeah, anything in between, if you use, like some tool to get the hex values for colors, you basically know what the values here are. I mean, not in detail, but, you know, not very nice. OK, so I said I wanted to classify a bit what, you know, the different parts in firmware and so on are. So let's see. I'm arguing that there are some systems which are interactive and some which are not interactive. And, you know, when we look at this laptop again, we know this is an interactive environment. But yeah, let's start with the non-interactive stuff. Like my watch here, for example, right? I actually never turned it on. I just bought it and put it on my wrist, and it was just running. I don't know. I'm just charging it. I did a setup at some point over my phone, but that's it. There is no installing your own operating system in this thing, right? So this is a non-interactive case, and that is actually what we have in many, many, many cases nowadays. But there are also some cases where you're not really sure if you can actually replace parts of the software. Maybe if you open this up, you could run your own, or maybe not. It always depends a bit. But yeah, arguably, this is a place where you don't really need a bootloader because, I mean, you don't put a USB drive in here, right, to install Linux or something. So this is running something really made for that. But yeah, then we have the interactive bootloader environments, like, you know, Grub that we saw earlier, or something that allows you to install your own operating system in many, many cases. Yeah, and as I said, you always need to be careful then again, because everything that is interactive means you're processing input from users, and user input processing always means you can have certain vulnerabilities in there if you don't watch out. Like when you interpret the dimensions of an image that somebody is applying. Or if people can run arbitrary commands, maybe you want to reduce the commands that are actually available. So what we want to do then is we want to offer a very rich user interface, so you can't really do arbitrary things, but still some nice things that you want, like changing settings, that can be like, I don't know, the boot selection, for example. On many PCs, you know this concept where you say, hey, I want my USB drive to be the first boot source, or I want the HDD, the hard disk drive, to be the first one, and so on. Or you can, I don't know, change the time or something like that, right? Now, there is also this concept of secure boot nowadays. I'm not going too much into detail whether the implementation is great or whatsoever, but these firmware menus, they nowadays offer you to supply your own data for key material and all of that stuff that you would use to sign your operating system. That is actually something very interesting to end users who really want to run something custom, but also lock it down from their side so they can be sure that it's not being tampered with. Well, and of course, if you want colorful graphics, that is how you get the fanciness of a graphical user interface, right? Yeah, I've also talked about this in a bit of a broader sense at FOSSIM a few years ago. So yeah, have a look at that talk if you're interested. OK, so another idea I had, I wanted to classify by application, right? So I already talked like, I don't know, wristband versus a laptop or something. That is one way. I'm looking at it in a more general sense, and that is the general versus special purpose thing. So general purpose means I have something that I can use in very, very many scenarios. And now I'm stepping a bit away from a specific machine, but I'm looking at actual code. So when I want to put my own operating system on a platform and my own bootloader or something, I need some options to choose from, right? Or, I mean, write my own, but there are already a lot of bootloaders out there, like Grub, for example. So if you want such bootloaders that you might author yourself or work on, if you want them to be distributed, like, virtually every Linux distribution usually comes with its own bootloader, right? Those bootloaders need to be designed such that they can be built in a very sane manner. They should be easy to distribute. I remember, like, I don't know, maybe 10 years ago, it was a bit of a struggle still when people tried to install Grub on their machine. Who has run a Grub command to install to their master boot record or something? And yeah, You might also have had a hard time, right? So sometimes it doesn't really work, and then you need to start over, and then you need to boot from a different medium again, and so on. It can be very hairy. So you want something that really always just works. Then, of course, we have special purpose bootloaders, like in this case, for example. I'm very sure that the very bootloader running on this thing here, that is probably something, but it's really just made for this one thing and not really universal, right? But there are some open source bootloaders that you may find, which you might need to customize for your specific use case. Daniel Mangum, also a famous engineer, has written a nice article about this for the ESP32, which you might know. It's very nice microcontrollers to work with. Yeah, so he explored a bit like, if you want to have your own custom bootloader, let's see what you can do with it. Yeah, I highly recommend to look into this. All right, and now with all of that in mind, let's see how it actually really works when I now turn on my computer. What happens? Well, the first thing in many platforms that we now have is you have some code that is already inside your processor. That is what we call a mask ROM. Some vendors call it boot ROM. It's a bit ambiguous because it doesn't necessarily say that's actually in the SoC, but yeah, it's usually what they mean. So, and how did that code in there? Well, it was written at some point, and during manufacturing, it was actually baked into all the transistors and whatever you have in there. Right, so that's how that works. Depending on the specific platform or vendor or something, it might also be called a zero-stage bootloader, for example. That is what the RISC-V ecosystem uses as a term. Those boot ROMs, they can be very, very interesting. Some of them, they offer very rich protocols. So I figured that, for example, on chips from the vendor Allwinner, if they are not connected to anything, they will offer you a protocol over USB. So you can run your own code just over USB. You can get very, very small development boards. You plug that into your laptop, you run a command, and then some code that you wrote will start running on that processor just over USB. Very convenient. There are others using other protocols, there is a processor series called JH7 something from another vendor called Star5. They have their own implementation. They use X modem. It's a protocol from the 70s, which is over serial. And then there are many, many other ways. Anyway, so this is really nice if you want to start with development. And now, depending, it's really different per vendor, per platform, per processor family, and so on. That really makes it very complicated to generalize it. And all I can say is you need different stages to run your operating system in the end. Okay, it really depends. So I'm not trying to classify that even further here. All I can say is the general thing is you have some firmware. Usually that is what initializes DRAM. Then you have your bootloader, and then your operating system. And well, now the thing is, if you want to run something custom, let's say on your laptop, for example, we need to have a concept of ownership. There are some laptop manufacturers that do not offer this as a feature. It's not something that many vendors actually advertise with. So usually it doesn't say like, hey, you cannot run your own code on this, right? Because, I mean, from a vendor perspective, it might also be okay to say, well, you can run your own operating system. They wouldn't tell you that you can't run your own firmware. You might figure this out, or there are some wikis out there which are trying to write this down, and so you know what to choose if you want to actually have something very custom. So yeah, let me dive a bit deeper into this early initialization that I talked about now, but I won't go too deep, just to have a rough understanding. So I talked about DRAM, and let's talk a bit about what DRAM is. So DRAM is essentially the many gigabytes of memory that you can have. Nowadays, you have like 8 or 16 gigabytes or something. They run at very, very high frequencies, right? So we're talking about thousands of megahertz nowadays. Some years ago, it was still some hundreds of megahertz, but now it's among the 1,000 or something. So it's in gigahertz reach now. That means you need to have controllers for it, which are very, very complex. They had a lot of research gone into them. So they were very expensive to make. And unfortunately, the vendors who are making them are not very open about them. So it's very hard, actually, to write your own code for them. If you look at some older ones, that is where you may find open code, for example, in a project called Coreboot. Well, now here is a small list of projects to look into. The first one is, well, everything around the UEFI ecosystem. There is one from Microsoft that is called Project Mu, and then there is another one that is called Tiano Core. That is like an umbrella project. So if you want to look at how most vendors implement their stuff, that would be like the common code base. And then usually they derive from that, and then every vendor has their own contractors again, and they build something on top of that. In Coreboot, well, we have open source code for a lot of memory initialization for older processors. Some people like putting Coreboot on their X230 laptops, for example. It's a very famous laptop from Lenovo. And it's very famous because that was actually the last generation for which we still had open DRAM initialization code. Very nice. I'm personally working on a project that is called Orboot. In Orboot, we have a boot part that is called BT0. It's like our first stage where we do DRAM initialization. Also, have a look at that. It's essentially a fork of Coreboot. And then, as I said, there is the famous U-boot bootloader that is for most embedded environments. That's how most people know that. They have something they call SPL for a secondary program loader, and on some platforms even TPL, that is for tertiary. That is what would be initializing DRAM on them. Yeah, and as I said, documentation is usually rather sparse. You might not even find anything. That always depends a bit on the vendor. If you know how that stuff works, in some regard, you might actually be able to understand some of the implementation. So even though we have some open source code for some implementations, you might still not understand everything without any prior knowledge, just because random stuff is written to random registers. Just as a bit of a warning, but I hope you're getting curious now, because now you want to figure out how it actually works. So yeah, as I said, many processors offer you some sort of protocol to talk to them in a very early phase. And so I'm listing a few tools here for development, because it's very, very convenient to do that sort of stuff. This is a non-exhaustive list. It's just what I've used so far. So there are some vendors for which there are some larger communities, like Allwinner, for example. They actually have a very, very nice wiki. Not Allwinner, but the community, and they looked at a lot of stuff. They reverse engineered a bunch. There is a tool called SunXi-fel, or SunXi-fel. FEL is the bootloader mode that Allwinner has. And then there are some other implementations of that. XFEL for some more modern platforms, and there is one written in Rust. Well, I'm not going to list all of them now, just so that you have an entry point. So if you buy a development board and you want to get started with that stuff, maybe you want to pick something from this list here. The bootloader itself can also provide an environment, to flash your own code onto some device. U-boot, for example, itself has a command that is called SF. I think it's short for spy flash or something. So that is how you would write to a flash part on your main board or your single board computer. And then Linux also has something which is called MTD. That is for memory technology device. That's essentially their driver for talking to flash parts. That is even available on some laptops. Like on mine, for example, I can look at a device. So do a short demo here. So I have something that is called def MTD0. So this is a 16 megabytes flash part that I have on this laptop here. And if I want to look inside of that, I can just use that device here. Very convenient. All right. With that, let's quickly run through a list of projects that we have. So I already introduced them a bit. So the Tiano Core project that I said, that is coming from the UEFI ecosystem. They have something that is called Dixie. I introduced that earlier. And then comes something that they call BDS. BDS for Boot Device Select. That is essentially then your bootloader on that platform. on some machines, you can actually replace that part because, that might be still that on those platforms it's not signed, so you can exchange the code for your own. I even did that on the Lenovo X270 at some point because, I figured out some way. So yeah, you can put a Linux kernel directly into that code, so, you would lose a lot of overhead that you would usually have, and then you can tailor something to your own needs. Yeah, usually devices come with something that is provided by the OEM, but yeah, it's a bit depending on the device or vendor whether you can replace things. There is a large community of so-called BIOS modders that you may find. There are some forums that you will definitely find if you search for this term, where you can have a look at what people already did with their stuff. Yeah, the U-boot bootloader that we know from embedded systems also actually has a very, very capable environment for interaction. There are some which are a bit reduced and locked down. That always depends a bit on the manufacturer. I saw that we actually have people from the Tourist project sitting in the front. So if you want to know about that stuff, I'm not sure, but they might actually be using U-boot. So you could also modify the platform. Yeah, U-boot has support for many, many different architectures. There is like RISC-V, there is ARM, and there's a bunch of others. I think it might even still have Spark or something in there, like a very broad portfolio. There are many, many different boards, even in upstream U-boot that are being supported. More than 1,000, I heard. I haven't counted them, but I'm sure. And, well, you can just boot Linux from it. If you want to know more about U-boot, I highly recommend watching those talks here. I think Marek is even also Czech, so yeah, he might even have given some talks in Czech if you're more familiar with the language. Yeah, one project that I work on, as I said, is the Orbit project. It is firmware written in Rust. We have the repository on GitHub. There is not too much in there yet. But you can use it for some of the currently available processors. So yeah, if anybody is interested, yeah, have a look at that, and yeah, you will also run into me on that project. Another one that we have is called Linux Boot, and that is what we then would combine with Rboot usually, and that is what gives you, as I said, an environment with drivers, and from there we can boot a full Linux operating system, like whatever distro you want or something. Yeah, it's very well known, so that is also why that is in use at many hyperscalers, like, AWS might use it, or Facebook, or Google, or something, because they can actually find very, very lots of engineers for that. Yeah. So yeah, here I want to give you a small example of a device that I told you could just plug into your USB port. And so what we did here is we created a system that boots in just a few seconds, connected to a USB port, and it gets up and running. And now you can use that as an extra CPU just next to your laptop. How cool is that? So this is what it looks like. What you see here on this very, very tiny screen, that is code that I ran from my laptop on that thing. We're using a special environment for that. If you want to look further, yeah, just follow me on the social medias and you will figure out more. I'm not going too much into detail here now. Anyway, yeah, this is a very, very cool platform. If you want to boot other systems than Linux, well, like let's say FreeBSD, for example, people have also done that. Warner Losh is the one who did this here. So he's using the Linux boot environment to boot FreeBSD. And if you are familiar with the BSDs, you know that it actually expects a bit more than just putting a kernel into memory. Right, so they also need modules somewhere in memory and stuff like that. I'm not even too much in the details here, but they have a bootloader that is called kboot, and that would be usually running in their own environment. But of course, you can also port that, and what they did here was they ported it to the Linux userland, so you can just run that command from Linux now. How cool is that? And well, I told you there are actually so many operating systems. Yeah, this is a bit of a tongue-in-cheek joke. What is my purpose? You might know the meme here from Rick and Morty. Well, doing something entirely, simple and stupid, not even, something rich you might be thinking of. So yeah, in this case here, I'm saying, hey, you're booting Plan 9. It's an operating system. I also happen to work on a bit sometimes. So yeah, how many operating systems do you know? Here's an even larger list of operating systems to look into, especially if you're studying computer science here, or I don't know, electrical engineering. You might also be running into this. There are so many operating systems, some especially made for teaching, like this one here, XV6, for example. It's a very tiny Unix-like system, which is really just for teaching. So was Minix, which is actually what inspired Linux eventually. So Linus Torvalds himself, was actually raised with the Minix environment, and then he said, I want to make my own. And then he did that, and now we have Linux, and it's running virtually everywhere. How cool is that? That could be you. So yeah, and there are so many more I'm not even going to talk about now. Now, with the last part, I want to talk about this thing called ownership. So what does it mean when you own something, right? There is also this sort of meme where they're saying, you're going to own nothing and you will be very happy with it. Yeah, there are different ways to talk about that. There might be some meaning behind that that isn't actually, that straightforward, but, more in a virtual sense or something. But, there is still this question, when you buy a laptop and you want to run your own stuff on it, should that be possible? I think so. So, yeah, I'm proposing to, talk about that stuff. So, first of all, if we want to fully own a device, what do we need? If we have a bootloader in the device that we can access, all good. We can at least run our own operating system. And that is usually the case on many, many platforms. So phones, for example, there are some which are locked down, but there are also some that you can unlock. I have this one here. I'm running Lineage OS on it. That was not the vendor firmware or the vendor system. I just put that on there because somebody figured out how to unlock that stuff and then, just made their own environment for it. That works on many, many phones. There are even people who, specifically buy a phone that actually is supported by Lineage OS because they want to have something that is, more familiar, more convenient, maybe not that much customized by the OEM who puts, I don't know what weird software in there which you cannot get rid of anymore, right? It might be that your firmware is signed, like on many laptops that we now have, like the Lenovo laptops, for example. They're using Intel platforms to lock down the laptops so that you cannot run your own firmware anymore. But there are also some where you can run your own firmware, like this one here. I'm really not advertising here, right? So yeah, if you want to read, you can read the brand name here. Anyway. Yeah, so if you want to run your own code, look out for that. There are some projects which are, using this mid-tier where you can replace part of your code, and that is what we have for many routers nowadays. For example, the OpenWRT project, very, very famous. On some platforms, they cannot fully run their own code, so they say, hey, do this and that, use the, the web interface, for example, you upload something, and then you replace the main part of the operating system. The firmware is still untouched, but you have replaced a big part. That gives you some ownership and maybe also nicer options than the OEM had in mind. And, usually that would also give you more support because many OEMs do not really give you much support after all. A similar project has come up for cameras that is called OpenIPC, also a very, very interesting project. I actually saw some of the security cameras here and there. So yeah, if you look at the OpenIPC project, they documented a lot of that stuff. And when you start looking into that, at some point you will recognize, there might be this and that chip in that camera here. Also cool. But why am I even talking about this? There is one aspect I find that is very, very, how do we put this? There are many people who are buying phones nowadays, and after 2 years, they already throw it away and get a new one, right? We all know it ends up in a landfill somewhere. And it might even be the case with many, many other gadgets that we have. It can be TV boxes or something, things that you buy off the shelf. They are very, very cheap. They're not very, very flexible in the end, as it turns out, and you might throw them away and try a different one or something. And then you've piled up a bunch of, well, electronics waste. right? That need not be the case. There are still many, many things we can do by just opening up the boxes, looking inside of them. Let's see what we can figure out. And that is something we're doing a lot in my hackerspace now in Essen. It's called ChaosPod. If you want to figure out more, yeah, you're welcome to follow me on the journey and see what we're doing. Yeah, 2 projects I looked into now were the Google Stadia controller. I was actually very happy at some point when they released new firmware because the project was killed. It was for running games, but on a cloud machine, so the game wasn't actually running on your premise, but you would have the controller for it. And at some point it was turned off, and now you have a controller with no use. So the best thing they could think of was they give you an upgrade so you could use it over Bluetooth and combine it with other machines again. Okay, good. There was a smart speaker in Germany called the Magenta Smart Speaker from Telekom, which had a similar issue. Their platform didn't really hit off. After a few years, they shut it down. That was just last year. Now you can get those boxes for €10 on eBay. So we bought a few of them. We started looking into them, and we're seeing if we can run our own code on it. No promises yet, but yeah. At least Telekom also offered an upgrade to a Bluetooth speaker, so now you would get a very, very expensive, it was originally €150. I believe in Czech crowns that would be times 30. So very, very expensive speaker with Bluetooth, right? Those which you could actually get for like, I don't know, 10% of that price. Anyway, better than throwing them away. Well, and as I said, there are many, many other devices which are similar in that regard. Yeah. And with that, I know this is a very, very big mouthful. I hope I could motivate you a bit to look into this stuff. I hope you found some aspects interesting. I see some nodding. Thank you. Very much appreciated. So thank you very, very much. If you want to follow me, you will find me all over the social medias and so on. Some recordings on YouTube and so on. And yeah, you will also find the slides already online there. And yeah, a similar talk I gave before. And now we're open for questions.
Yes. Any question? No. So thank you very much.
Yeah, thank you too.